In this chemistry tutorial, we're going to look at ionic bonding. The first aim is to define the term ion and explain how bonds form between ions, then explain how to write ionic compound formulae, and then finally explain the properties of a giant ionic lattice. Now, undoubtedly, the most well-known ionic compound is sodium chloride, commonly known as table salt. Sodium chloride is found naturally in seawater, and we can evaporate the water to extract the salt. But we can also make sodium chloride in a lab, and this process is far more revealing in helping us understand how ionic bonds form. So I'm just going to show you a quick video clip where I'm going to react the metal, the very reactive metal sodium, with the pale green poisonous gas called chlorine. When they react, the reaction is so hot that the salt is actually present as a cloud, a gas of salt, which then cools to form crystals of salt. You can see this yourself now. So now they're reacting. And then given time, the salt gas condenses and you're left with solid crystals of table salt. But what is ionic bonding? If you translate it literally, it kind of helps you understand. Ionic, meaning ion, meaning charged atom. So an ion is a charged atom. It can either have a positive or negative charge. And a bond is a force of attraction. Much like the North Pole and South Pole of a magnet attract each other, you feel the force of attraction. Well, these forces of attraction occur over much smaller distances. So we can describe ionic bonding as a force of attraction between charged atoms or ions. As metals contain positively charged ions, I thought it would be a good opportunity to introduce the idea of metallic bonding here. This is not the same as ionic bonding, but you do need to know it for your exams. So if I remove the gold bar and we can see what's going on inside, you'll see that metals have a very unique structure. Unlike in nonmetals, where you have a positively charged nucleus due to the presence of protons, and then you have the electrons in orbits in those shells whizzing around the positively charged nucleus, in metals, the electrons are delocalized. What that means is they're free to move away from the nucleus. They can actually move like a sea of electrons through the structure. So if you have to describe metallic bonding, you can say positive ions in a sea of electrons, or in an electron sea. That is a technical term you can use. Positive ions are also referred to as cations. So take note here, an atom stripped of all its electrons in the shells forms a positive ion because you have a charged particle there, a positively charged nucleus. And because electrons are free to move throughout this structure, it does explain why metals are very good conductors of electricity, because these charged particles can move. That's what an electric current is, when charged particles move. And also why they're good conductors of heat. But that's metallic bonding. What about ionic bonding? Ionic bonding occurs between metal ions and non-metal ions. Metal ions are always positively charged, and we call them cations. That's why I've drawn a cat here. Non-metal ions are always negatively charged, and they are called anions. Because it looks and sounds a bit like onion, I've drawn an onion here, but you do pronounce it anions. And because positive and negative ions attract each other due to their opposite charge, there's a force of attraction there which holds them close. So let's look at a quick recap regarding how atoms actually become charged and form ions. You can use the periodic table at the front of your exam paper to really help you get a head start with this topic. To understand ionic bonding, we only really have to look at 4 groups. Group 1, the alkali metals. Group 2, the earth alkali metals. Because they're metals, they'll form positively charged ions. Group 6, non-metals. And Group 7, the halogens, which are also very reactive non-metals. 6 and 7, being non-metals, will form negatively charged ions, or anions. All group 1 elements have 1 electron on their outer shell. That's why they're in group 1. That's what group 1 means, 1 electron on my outer shell. Now this makes group 1 very reactive because they just need to lose that outer electron and they benefit from a complete, stable, full shell underneath. So group 1 metal atoms become ions by losing 1 electron. Group 2 metals have 2 electrons in their outer shell. That's why they're in group 2, and they form ions by losing 2 electrons from their outer shell. This also gives them a full shell underneath. Group 1 and 2 will lose electrons to complete their outer shell because it's much easier to lose 1 or 2 electrons than gain 7 or 6 to complete their outer shell. Group 6 elements have 6 electrons on the outer shell. That's why they're in group 6, and to complete their outer shell, they will gain 2 electrons. And now you can see they have 8. And you've probably figured this by now, but group 7 have 7 electrons on their outer shell, so all these elements have 7 electrons, and they just need to gain 1 more electron to become complete and stable, so they will receive or gain 1 electron. So that's what they do, but why does this make them charged? Let's take an example. Let's look at lithium from group 1. Lithium has an atomic number of 3. You can see that over here, lithium atomic number 3. What that tells us is that lithium has 3 protons, 3 positively charged particles in its nucleus, but it also has 3 electrons in its shells, negatively charged. Because there's 1 negative charge for every positive charge, the overall charge of the atom is neutral or 0, because protons and electrons have equal but opposite charges. Now we know that group 1 elements must lose an electron when they form ions. So by losing that electron, what happens is we now have 2 electrons in the shells, but 3 positively charged protons. So now we have 1 excess positive charge. So we write a lithium ion as Li+, because it has a single positive charge due to this single excess proton. All group 1 elements will form single positive charge ions. For example, Na+, sodium would form an Na+ ion, potassium a K+ ion, rubidium a Rb+ ion. Now let's look at a group 2 element. Here we're looking at beryllium with an atomic number of 4. That means it has 4 protons in its nucleus and 4 electrons in its outer shell, so the overall charge of the atom is 0. Beryllium, like all group 2 elements, will lose 2 electrons to form an ion. So as you might expect, this upsets the balance of electrons and protons. So now we have 2 excess positive charges. So a beryllium ion is written as Be2+. Notice how the number comes before the charge. Number first, then charge. So all group 2 elements form 2+ ions. Magnesium ion will be written Mg2+, a calcium ion will be Ca2+. And that's because they all lose 2 electrons, leaving them with 2 excess protons. Now let's look at the group 6 element, oxygen, which has an atomic number of 8. That means it has 8 protons in its nucleus and 8 electrons whizzing around in the shells. Now oxygen forms an ion by gaining 2 electrons to complete its outer shell. All ions have complete outer shells, remember that. So now it's gained 2 electrons. This means there's an imbalance between the number of protons and electrons, but this gives oxygen a charge of 2-. Remember, the number first, then the charge. So all group 6 elements, because they all gain 2 electrons, gain a charge of 2-. So an oxide ion is O2-, a sulfide ion is S2-, etc. Notice with non-metals how I don't say oxygen ion, I say oxide ion, and sulfur, I say sulfide ion. That's something you'll have to remember, that you have to end non-metal ions with IDE. Finally, if we look at fluorine, which is an example of a group 7 element, fluorine has an atomic number of 9. That means it has 9 protons in its nucleus and 9 electrons, balancing those positive charges in the shell. So the overall charge of fluorine atom is 0. But when fluorine forms an ion, it needs to gain 1 electron to complete its outer shell. This also upsets the balance of charge. Now we have 1 extra, a negative charge. So you've probably figured this out by now, but a fluorine ion is F-, because it has a negative charge of 1. Similarly, all group 7 elements, the halogens, form negatively charged ions with a 1- charge. So chloride ions would be Cl-, bromide ions, Br-, iodide ions, I-. Notice again how I replace the INE in fluorine, chlorine, bromine with IDE to describe the ion. So now we understand how ions form. Let's understand how ions bond together. An ionic bond always forms between metal and non-metal ions. And more specifically, metal atoms transfer the electrons on their outer shell to non-metal atoms. So you can see this metal atom, which represents lithium, has 1 electron on its outer shell here, and this non-metal atom, which represents fluorine, has 7 electrons on its outer shell. So they're both very close to getting a complete outer shell. All that lithium needs to do is get rid of that outer electron by transferring it. So it transfers it to the non-metal atom. By doing that, it loses its outer shell and gains a complete outer shell which was underneath. In doing that, it also becomes charged. So we have a lithium ion with a positive charge because it's lost a negative particle. Fluorine, having gained an electron, gains a charge as well. Fluorine will pick up 1- charge because it's gained 1 electron. Because they have opposite charges, they will attract each other, and that will form the bond. So that is how we define the term ion, a charged atom, and explain how bonds form between ions. So now let's look at the most complex part of the tutorial in my opinion, how we name ionic compounds and how we write ionic compound formulae. Remember that an ionic bond forms between a metal ion and a non-metal ion. I've got two examples here, so I have sodium and calcium representing our metal ions and oxygen and iodine representing our negative ions, just randomly chosen. Now when they react, sodium and oxygen will form sodium oxide. Notice how we end it with IDE. Similarly, calcium and iodine form calcium iodide, again ends with IDE. When two elements bond ionically, we use the ending IDE. You actually get assessed on that in exams, so remember that point. Also, notice how I've written these in white, but these are pink and these are blue. The pink in this tutorial represents positively charged particles and the blue negatively charged particles. When they react, the charges balance out again and therefore the compound will lose its charge. So you don't get ionic compounds with a charge, they become balanced. So that's why there's no charge here. You also need to be very aware that some non-metal compounds can form negative ions or anions too. The four you need to know are hydroxide ions, which form OH-, nitrate ions, which are NO3-, carbonate ions, which are CO3 2-, and sulfate ions, which are SO4 2-. Be aware that the 3 here doesn't represent the charge. The charge is the thing in superscript, not subscript below the O. So nitrate ions only have a charge of 1-, not 3. I've seen students make that mistake. Similarly, carbonate ions have a charge of 2-. The 3 just tells you how many oxygens there are, and the 4 just tells you how many oxygens there are in this compound, but the charge is 2-. Don't get these numbers muddled up or confused. They mean two different things. So when a metal, any metal, reacts with these non-metal compounds, naming them is actually quite easy. For example, you just say lithium hydroxide, or you say lithium nitrate, or lithium carbonate, or lithium sulfate, or whatever metal you choose, calcium hydroxide, sodium hydroxide, copper nitrate, for example. The key learning point here is any ionic compound that contains a non-metal component which contains 2 or more elements, including oxygen, usually ends with 8. So you can see here the non-metal compounds, 2 or more elements containing oxygen, so nitrate contains oxygen, we end with 8. Same goes for carbonate ions, ends with 8 because we have a carbon bonded to an oxygen, and sulfate because we have a sulfur bonded to an oxygen. The only exception here is hydroxide. There are always exceptions to the rule in chemistry, I'm afraid, and hydroxide is referred to as IDE, not 8. But other than hydroxide, all the others end with 8, and in an exam you need to be able to distinguish between compounds ending with 8 and those ending with "ide." Just remember hydroxide's a bit of a swerve ball. But the most sophisticated part of this is understanding how we write ionic compound formulae. Why do we write sodium chloride as NaCl, but magnesium chloride as MgCl2? Why is calcium oxide CaO, but potassium oxide K2O? And why on earth does magnesium nitrate look so fiendishly complex with brackets and everything? There are in fact very good and logical reasons for all of this, and I'm going to explain this now. So in this table I have group 1 elements that need to lose an electron to become stable and have a complete outer shell, and they all form +1 ions. We have group 2 elements that need to lose 2 electrons and they form 2+ ions. We have group 6 elements which need to gain 2 electrons, so they form 2- ions, and group 7 elements which need to gain 1 electron, so they form 1- ions. I've included these in a different colour because they are not members of group 6, because they are not elements, they are compounds, and same with this one here. But because carbonate and sulfate ions need to gain 2 electrons to form an ion, and because nitrate ions need to gain 1 electron to form an ion, I've put them in the groups according to their similar need. So let's start off with the easiest part. You can see that group 1 elements need to lose that outer electron, and group 7 elements need to gain 1 more electron. So group 1 and group 7 are a match made in heaven. For example, let's say this is a lithium atom. That lithium atom just needs to give its outer electron to a fluorine atom, and now we have a lithium ion and a fluorine ion. And that forms the compound, or the ionic compound, lithium fluoride. Notice how I have not drawn a charge on the compound because they balance each other out. There is no charge, it's neutral. Ionic compounds are always neutral. Similarly, Group 2 elements need to get rid of 2 electrons, and group 6 elements need 2 electrons, so they're another match made in heaven, because all group 2 have to do is give their 2 electrons or transfer their 2 electrons to group 6 elements. So here we've made a beryllium ion and an oxide ion. So we'd write the chemical formula for beryllium oxide as this. Once again, the charges are balanced, so it's neutral. So group 1 with group 7, easy. Group 2 with group 6, easy. Where it gets a little bit more complicated is where we react group 1 with group 6 or group 2 with group 7. So here we have a lithium atom with 1 electron to give, and we have an oxygen atom which requires 2 electrons. So instantly there's a problem, because obviously lithium can give that 1 electron to the oxygen, but it's still not satisfied. It still needs another electron. So where does that come from? The answer is it comes from another lithium atom, because then you have the 2 electrons necessary to complete the outer shell for oxygen. So you need 2 lithium ions to bond with every single oxide ion, because it takes 2 lithium atoms to provide the necessary amount of electrons to fulfill oxygen's outer shell. This is why lithium oxide is written as Li2O and not just LiO. This rule applies whenever you're reacting a group 1 metal with a group 6 non-metal. So lithium oxide is Li2O, sodium oxide is Na2O, potassium oxide is K2O. So now let's take a look at what happens when you react a group 2 element with a group 7 element. In this example, let's use beryllium with fluorine. Now beryllium has 2 electrons on its outer shell because it's in group 2, so it has 2 to give, but fluorine has 7 electrons on its outer shell and therefore only needs 1. How do you solve this problem? Well, you can certainly transfer 1 electron, but then you have a problem because the electron shell is full. Perhaps you've guessed, but you will need another fluorine atom to mop up that extra electron. So now beryllium can give away its last outer electron and benefit from the full shell underneath. The shell does disappear, it doesn't just stay there. So every beryllium atom will require 2 fluorine atoms to react with, because 2 is the necessary amount to take the 2 electrons which beryllium has on its outer shell. So when you write beryllium fluoride, it looks like this, BeF2. And you can apply this logic to anything from group 2 reacting with anything from group 7. So beryllium fluoride, you know, magnesium chloride, MgCl2, calcium iodide, CaI2. But what do we do when we're factoring the use of charged compounds like carbonate ions, sulfate ions, nitrate ions, and hydroxide ions? Well, the logic is exactly the same. Let's take something simple like magnesium with carbonate. Well, magnesium forms a 2+ ion because it gives away 2 electrons, and obviously carbonate ions require 2 electrons, so they react happily in the ratio of 1 to 1. So you can just write magnesium carbonate as MgCO3. Similarly, if we take anything from group 1 and we react it with a hydroxide ion or nitrate ion, lithium forms an ion because it needs to get rid of 1 electron, and hydroxides form ions by gaining an electron, so again they react happily in the ratio of 1 to 1. So we write lithium hydroxide simply by going LiOH. But what about something a bit more complicated? Let's take magnesium and let's take nitrate. Now magnesium forms a 2+ ion because it has 2 electrons to give away. But nitrates can only accept 1 electron. So how do we solve this? Quite simply, we need another nitrate ion to receive that extra electron. The tricky bit is understanding how we write this. So we write Mg, and then we want 2 nitrates. So we write NO3. But if we put a 2 here, we have a problem, because this is saying 32 oxygens. That's not what we mean. We just mean double the nitrate. The easy fix is just put brackets in. And when we put brackets, now we're saying that everything inside these brackets is doubled. We need twice the nitrate. Let's try one more fiddly one. Hopefully you're getting the hang of this now, so maybe you can work this one out without my help. So pause it and give it a go. But how would you write the ionic compound formulae for calcium hydroxide? Well, calcium forms a 2+ ion by getting rid of 2 electrons. But hydroxides only require 1 electron to become stable. That's why they have a charge of OH-, telling us they receive 1 electron. So the solution is, again, we require another hydroxide. So calcium hydroxide is written CaOH, But once again, do not just write a 2 there, because that will only apply to the hydrogen. We want it to apply to the oxygen as well, so once again, we use brackets. Now that you understand this, there is a shortcut you can take. If the charges are perfectly balanced, equal and opposite, then the elements will react in the ratio of 1 to 1. So lithium fluoride is LiF, sodium chloride is NaCl, and magnesium oxide is MgO. Because the charges are balanced, you do not need to add any little numbers anywhere. However, if there's an imbalance of charge, for example, I have 1 plus charge with potassium but 2 minus here, that means we need double the positive to balance out the 2 negative here. So we need 2 potassiums, and those 2 positive charges will balance out with the 2 minus charge here. So potassium carbonate is written K2CO3. You do not need brackets around the K because it's just a single element by itself. Brackets are only needed when you're scaling up more than one element at a time. Finally, if you look at calcium, 2 plus charge, Br minus 1 minus charge, that means we need to double the amount of negative charge to react with calcium. Having double the charge, now they are balanced, 2 plus, 2 minus. So calcium bromide is written like this, CaBr2. You could pause this screen and just have a play around with trying to work it out and get some practice in. And that's how we explain how to write ionic compound formulae. So the last part is looking at ionic compound structure. All ionic compounds form giant ionic lattices. If you look at ionic compounds, they always appear to be very angular with sharp edges, so you can sort of imagine what their structure might look like. It must have a regular arrangement. So let's have a look at a giant ionic lattice. This is how we imagine they look. Ions of opposing charge held together in a regular arrangement. In exams, if you have to describe the structure of ionic lattices or ionic compounds, you would say closely packed ions of opposing charge, positive next to negative, negative next to positive, in a regular lattice arrangement, in other words, in nice rows. The ions are held by very strong electrostatic forces. That means forces between charged particles, positive, negative. This is a handy definition to memorize. So now we'll do what chemists do best, which is relate the structure of a material to its properties, to how it behaves. Now, because of these exceptionally strong forces of attraction represented by these white lines, these are the bonds between the ions, giant ionic lattices have a very high melting point. You could put them in a frying pan and heat them up, and you could be waiting there all day for them to melt. And that's because of the very strong electrostatic forces of attraction between the ions. You see, you need to invest a lot of energy to break those forces of attraction. Giant ionic lattices, however, are very soluble in water. If you've ever put salt into water, you'll notice it dissolves very quickly. And also, they conduct electricity when molten, that means melted, in a liquid state. This is a state symbol. L means liquid, small l, not capital. Or dissolved, that means dissolved in solution. We give dissolved substances an AQ. So if you put salt in water and mix it around, you would have an aqueous form of salt. It will be dissolved. Exams really like to test you on this. So the question might be, why do ionic lattices conduct electricity when melted or dissolved, but not when solid? Here's the answer. It'll be for about 3 marks. Firstly, understand that an electric current is a movement of charge. It's when charged particles move. Now, if you're fixed in position in a lattice, yes, there's lots of charged particles, lots of ions which potentially could conduct electricity, but they're frozen, they cannot move. So without them moving, there's no electric current. So ionic compounds cannot conduct electricity when solid because the ions cannot move freely. However, if we melt this structure, then the ions become separated and are free to move, or we dissolve this structure, then again the ions become separated and are free to move. Now they can conduct electricity. So if I put my circuit with 2 electrodes into this substance, and similarly here, the light switches on because they can conduct electricity. We have moving charge. You see, the positive ions are attracted to the negative electrode, and the negative ions are attracted to the positive electrode. Incidentally, this is why they're called anions and cations. The positive electrode is called the anode, so anions are attracted to the anode, and cathode is negative, so cations are attracted to the cathode. Positive to negative, negative to positive. But in an exam, you just need to write, when molten or dissolved, the ions are free to move, so they can conduct an electrical current. So that is how you explain the properties of giant ionic lattices.